Okay, good morning, everyone.
Good morning.
Like the second week. Okay. So yeah, yeah. As I mentioned, as I mentioned on the first day, I won't talk about the problems yesterday now in detail. We'll do it on the Saturday, but yeah, probably cover now explicitly mention which one are intended to be topic related, which one are taken from other contexts. Yeah, so yeah, but you probably have figured it out already. And some of the tasks actually, even in the task that I prepared intended to be topic related, can be solved with other stuff as well. So yeah, yeah, many ways to solve it fast. And yeah, I tried to randomize the order, but random the clarity gives me not so very good random. Like yeah, like all the topic related tasks are in the later half, and yeah, this becomes complicated. So the problem becomes harder on the beginning of the task. But yeah, it's just you never know what you get from randomizer. Okay, yeah. So anyway, so today we're going to talk about. Yeah, today, as mentioned in the first day, we're going to talk about some DB optimizations, and some of these optimizations are actually applicable to non-DB as well, but they are usually used in DB. But yeah, we'll see later. Yes, and some of these stuff I probably guess some of you have already know, but yeah, we'll still go through it, and some of the tasks will be hopefully interesting for you as well. So yeah, as usual, make sure you can read this line. As usual, let's talk about some limitations. Of course, before optimizing it, I hope you already know. This is quite basic. So you're on this class, you should already know what it is. And some of the stuff recently are. And then yeah, we're going to talk about contextual optimization. So I hope you know what contextual is, at least the basic idea. And then we're going to talk about optimizing DP with defined conquer as well. So I hope you know what defined conquer is. Yeah. Again, if any of this is not really familiar for you, please ask. Okay, so let's start simple with DP optimization that is usually not so often discussed because it's just another DP, standard DP, but I can give you some examples. So some problems usually require you to reverse the state and the answer. So yeah, you usually when you have a DP where the values of the state can be large, but the answer is small. So you usually reverse the state and the value. For example, like let's say you are given a standard 0-1 exact problem, right? But the weight can be large, but the values are small. Usually, usually you knapsack solution, you do a dynamic programming where the state you use the weights as a state, like how many values you can take if your back capacity is W, right? So, but this does not work because the failure of W in this case can be large. So what you can do is the failure is small. So what you can do is instead of doing that, you can reverse the DP, right? So now your state is just total value, and now you're computing what's the minimum weight required, minimum total weight required to take at least this value, right? Or not at least, exactly this value, right? So this is a standard DP with weight, right? And yeah, because it's a 0-1, I hope you know that we can have just one dimension by routing the opposite direction. If you reverse this direction, 0 to W, it becomes not 0-1 knapsack, but you can take each item multiple times. Does that make sense to you? Yeah? Makes sense, right? Okay, so yeah, you don't need to have the second dimension for the I, you can just use this. Okay, this is a standard. You either not take the ith item, or you take the ith item and the remaining weight becomes x minus p wi. This should be j, not x. Okay, yeah, but you get the idea. This should be j. Yeah. And then plus pi, yeah, because the value increases. Now, because we want to refers the DP now. Yeah, let's say DP2 is the one that I mentioned earlier. What's the values? The maximum values you can get now becomes whether, yeah, now you look from the maximum value that you can get, which is the sum of VI. And then, yeah, if you don't take the item, still remains this. Otherwise, yeah. So now you try to minimize, right? Yeah, correct. Yeah, so if you choose the item, it becomes, yeah, you take from the x minus pi, but the weight now increases by wi. Okay. Yeah. So yeah, then now the answer is usually just called dpw. Now you have to look actually to find what is the maximum v, but still the dp2v is still less than w, right? Because you only have back of capacity w. Right, so you have to look and then find this. Okay, so now the time complexity becomes n times some vi, but just now vi is small, so vi times n is still, vi times n squared is still small. Okay, yeah, it should be quite straightforward, just for more this video. Okay, yeah. Now next, yeah, we're going to talk about some convexual optimization. Yeah, so again, it's not specific for DP, but usually used for DP. Yeah, so I guess this is the generic how we do convexual trig convexual optimization is when there is a, this is the like the standard formulation where you have several lines. It's represented by mx times to be c, but okay. Whatever. Yeah, but basically standard line. There's a gradient. There's a constant, right? And then there are several queries. The question is, you are given a value x, and then we want to know among the n lines that we have, which line is actually minimum at x equals xi, right? So if we like, so you have several lines like that, and then let's say we have xi here. So we want to know which line we hit first from negative infinity, right? So it can be different throughout different values of xi, right? So it's either this one, it's here, yeah. So that's the basic thing that this is the thing that we're trying to solve with convexual optimization, convexual trig, right? Okay, and we'll show you. I'll show you some examples where this can be used to optimize on DP. And there are lots of problems like that. Some of you have probably solved it before as well. Okay, so yeah, the idea how to, of course we want faster than n times q, which n times q is that. Yeah, so the idea is each line can be the minimum, can be the answer for contiguous values of x, right? So yeah, let's say why there are these lines? Never mind this line. I need to remove this. Okay. Yeah, so yeah, this is the image taken from WC. It's a great reference for this topic as well. So yeah, let's say there are these lines. So yeah, basically, yeah, each of these lines is drawn differently, so you know which lines is which. And yeah, you see that the green line here is the upper half. Yeah. And then yeah, you can see that basically this is the line that can be the answer when you query x equals xi. So if you query here, let's say the answer is this one. If you query here, the answer is this line, and so on, right? And you see that this line is only minimum from this x to this x, right? And it's a contiguous interval. And in this case, yeah, let's say x may be negative as well, so this can be unbounded. So all the way to x equals negative infinity, this is still the minimum line, right? Yeah, so that's the idea. So yeah, once we know the interval endpoints, we can answer its query using binary search. So we want to be able to find the endpoints of these intervals, and then once we store that in a factor, let's say, then just if x is here, then we want to know which endpoint is the, like, let's say the writers are still lower than x. So it's here, so you know that it's this line, and you can get the which line is the most optimal, right? But now the other part is how to find the interval endpoints, how to actually get this green line, right? So yeah, okay. Not that the upper hull, the minimum line has a decreasing slope, so it's like form like the upper hull of a convex hull, right? And then yeah, so the idea is similar to ground scan. If you're familiar with how to find a convex hull in a polygon, in 2D polygon, we sort the lines by slope, by gradient, and maintain a stack. Okay, in ground scan you find the most minimum y point, and then you sort by slope, and then you keep a stack. If it turns the wrong way, you remove the last point. Yeah, it's very similar. Yeah, basically you keep popping lines from the stack if they are obsolete. And yeah, here, so if we keep the lines by slope and we sort it decreasing slope, so this line will be first, this is second, this is third, and this is fourth, right? Yeah, so but we see that these lines is when we have these two lines, right? The optimum line will be this and then that, right? And when we have this line, the third line, yeah, we know that we can see that this line now becomes obsolete because they are not part of the optimal solution anymore, right? So we remove it from the stack. So it's similar. So you have this line, and this line. So this is on the top of the stack. This is on the second top, and then this is what we are going to push to the stack. And we know that the line on the top of the stack is obsolete. We pop it from the stack, right? Okay. Yeah, and yeah, as usual, let's create the class first. Just line M and C, right? And then yeah, we just create a tag there to make it easier later to find the y value if we give it x. Yeah, so the idea is that yeah, you create this is a simple obsolete method. So let's say we're going to call this with B is the one that is on top of the stack. A is the one on the second top of the stack, and C is the one that we're going to push into the stack. So basically, yeah, the logic is that if, so let's say this is A, this is B, and this is C. So we find the intersection point of A and B, and the intersection point of A and C, right? If the intersection point of A and C is to the left of A and B, then we know that this line is actually useless, right? But if this is to the right of this, that means that this line is actually still optimum, right? For a bit, and then it goes down. Right? Does that make sense? Right? Okay. Yeah. So yeah, basically, yeah, this is standard geometry. You find the intersection point by because we have y equals mx plus c. If we have this, and we want to find these two, we want to find the intersection of x, then becomes what? Because this is x equals basically because we want to find a common point, this y1 and y2 will be the same, so we get something like this, right? And then we solve for x, right? C2 minus C1 divided by M1 minus M2. Yeah, okay. So yeah. So yeah, there you got intersection of AC, AB, and then yeah, you can avoid the doubles by doing this times the other one, like and then to find out whether this is smaller than you get it, right? Okay. Yeah. So okay, and then yeah, how to use this obsolete method is a standard. Like a gram scan, like you sort. Yeah, assume the lines have been sorted by M, the field of M, and then yeah, while you can pop back while the top of the stack is obsolete, you pop it, right? When you keep popping back, if it's not obsolete anymore, then you don't pop it and break, and then you insert the lines the lines to the stack, right? Okay. Yeah. So oh yeah, we don't actually want to use stack. We usually just use factor, but when inserting, we treat it like a stack. Yeah, again, because when we query, we want to binary search, and if you use actual stack, we cannot do that, right? So yeah. Okay. Any question after this point? Yeah, again, I'm sure some of you already already know this, so just okay. Okay, so yeah, an example problem. Yeah, this is quite a classic problem when we talk about this. But yeah, in case some of you are not familiar, I'm going to show how this is useful for optimizing dynamic programming. So the problem is, yeah, let's say you're given an array X of n integers, and we want to partition, and each of them has to be a contiguous sub-interval, such that for each partition there is a score there, and the sum of the score of each partition is maximized, right? So the score is A times, so ABC is a constant given, and the score is A times sum of the element square plus bx plus c, right? Okay, and this is the constraint. So yeah, yeah. So this is the constraint, and of course, if you're familiar with DP, and I think you are, this is very straightforward with S squared DP. Sorry.
Go back to the problem.
Sorry. So basically like this, and then let's say we partition here, then whatever sum is this, let's say A, we get HK squared plus BK plus C from here, this is the sum. And then let's say this is L, we get AL squared plus BL plus C here, and then the same thing here, yeah, and then we total this, and we want the total to be maximized. Okay? Yeah. Okay. Yeah, of course there is a simple DP where if let's say DPI is, you only consider the first I element, okay, and you want to answer DP n minus 1. Sorry, let's assume this is one base. You want to answer DP n. DP 0 is 0 because there's no element, right? Empty set, empty array, and DPI is just we want to find out where is the optimal cutting point, right? And by cutting here, we'll get these points, A whatever, and then here we can still cut again in DPJ, right? Plus this, right? And yeah. Okay, yeah. So max J, find the J. This is J minus 1. If you also this is J. Okay, so yeah. Just and then we use prefix sum to find the intervals sum the sum in the middle from I to J quickly, right? Okay, this should be standard. So now yeah, let's say because typing pre is too long, let's just say Pj minus 1, which is this prefix sum is Pj, and then this is Pi. Right? Okay? And yeah, I just write the formula again. So basically, we want to find a J such that dpj minus 1 plus the score that we get from this is maximum, right? And we can expand the square a bit. And yeah, we can see that we can group this, some of these terms together. Okay? So yeah, you can see that the purple one is constant. It's just dependent on J, does not depend on I. And the green one is only dependent on I, does not depend on J, right? And that's the nice part, because then whatever value of J, yeah, we can just do like the Pi is something like this green term, plus you minimize the J here, right? So it's whatever J, it's I, the I is constant. So when you have this DP, then this term is nice. Because you don't need to worry about that for the finding the J part, right? Yeah, but then yeah, if there's no red part, if it's just this and this, then you don't need convex sum. It's just when you complete your DP, you from 1 to n. You also store which value of j has the minimum value of this, right? Maximum, sorry, yeah. Maximum value of this. So when you compute dpi something, and then you, let's say, res equals max res dpi. And then for the next dpi is just res plus this, right? Yeah, okay. So if there is only this and this, it's simple. But now there is this part as well, and this part depends on both I and j. Now we cannot do this anymore because now the j, whatever j value we choose is also depends on the current I. Right. So yeah, but here you can see that yeah. So if we say so yeah, we try to the part in red, we try to split out which part is depends on I and which part depends on j, and we factorize. So we try to get like in terms of mx, where m only depends on j and x only depends on I, right? Okay, and in this case m is minus a times 2 times pj, or actually you might be able to put the 2 in pi as well. That's also fine, or the a as well. Now if you put the a, there's complications later, but you can actually take out the 2 to 2 times pi, and then the m becomes minus a times pj. That will also work. Yeah. Okay. Yeah. So yeah, then the c is just something that is constant on the value of j. That does not depend on it. Okay, so if we insert this line, so after we finish computing the dpi something, right, we insert this line, right, with m equals minus a times 2 times pi, and c is this one, yeah, okay. And when you do that, for the next value of I, we can use this line to query the x using pi, right. So if we use x equals pi, we can get the optimum j such that yeah, mx plus c is maximized. Yeah. Does this make sense? Okay, yeah. And here the interesting part about this problem is that the value of a earlier is must be negative. That's the constraint of the problem, right? And pj is also increasing because the prefix sum of a positive sequence is always increasing. And in this case, x is also, the array is also increasing. Sorry, it's also positive. So the prefix sum can be only increasing. So here, this value can only, this m can only increases, right? Yeah, that's why I say the a must be in the m, cannot be on the x, because otherwise the gradient will decrease, right? And because this is a maximum problem, just now I showed the minimum problem. When we try the minimum, we solve the gradient we try to solve the gradient decreasingly, but if it's maximum, then we want the lower half instead, right? So we solve the gradient increasingly, right? So in this problem, it's just nice. When we go from dp1 to dpm, the gradient will be already increasing, so it's nice. We will add the lines already in the increasing gradient, right? Okay. Yeah. So yeah, pj, this is positive, this is increasing. So yeah. Okay. Now the query, which is pi, the x value, is also increasing. Again, because the prefix sum is also increasing. So we don't actually need binary sorts for this problem. Can you answer? Do you answer? How can we avoid binary sorts? Sorry? 2 pointers, yeah. So, well, having a stack, we also have another pointer which starts from the front as well, which stores the query. Like, because we know that the stack has increasing gradient, and the query also has increasing gradient. We can, while the earlier pointer is lagging behind, like we check whether increasing the pointer actually gives us better value. well, it gives us better value, we keep increasing, right? Yeah, so, and then we know that for the next query, the value of the query, the value of x is increasing, right? So this is y, this is x. Let's say the current query is here, we know that the upper hall is something like this, and the next query, the x is increasing, so we know that we can only go forward in the stack of optimum lines, right? So yeah. Okay. So yeah, in this problem, and I don't know whether n log n will pass because n is 1 10 power 6, and this is from 2010, 13 years ago. Readers back then were slow. I think. I don't know whether this n is intentionally made to be. You have to do ON. But yeah, there's a ON solution for this problem. Yeah. Yeah. No, usually it's not. Usually log n factor is doesn't matter, but yeah, sometimes it is. So yeah, you can see that in some of these problems, actually, this must be increasing. So some of these things must be increasing. So you don't actually need very short or some complicated conventional method. Okay, so yeah, this is ON. If you type this on Facebook Messenger, it becomes something like this. Yeah. Okay. Now there's another extension. It's called the fully dynamic variant. When the gradient might not increase, right? And let's say, so you can add lines, and when you add lines in the middle, there can be online queries, right? If it's offline query, then even though the lines is not sorted, doesn't matter. You can just sort after all the add is finished, right? But let's say it's online where there can be lines added, and the gradient might not be monotonic, right? So it's up now. You cannot solve with the previous stack method, right? So yeah, because you might need to, like, after you find this hall, there might be a line that's like this, and then you have to go back many layers of the stack, yeah, right? So you cannot do that. You need the extension. So yeah, basically, yeah, find where the line should be based on the gradient. This is basically similar when you given a query X, right? So you do binary search, and then yeah, we need to remove obsoleted lines to the left and to the right of that line, right? And because we want to remove elements in the middle of a stack or a vector, whatever, we cannot use vector anymore. So even vector is not strong enough, it's not good enough. We need to use STD set, right? So yeah. So yeah, basically. So if there is a line that looks something like this, yeah, we need to be able to remove this line, right? And it might be this to the left as well. Yeah. So actually not necessarily. Let's say this bottom like that. Then we need to move. Yeah, you get the idea, right? Okay. Yeah, we need to remove some. Yeah, but the idea here is that we can only, from where this line should be in terms of the gradient order, we can only remove several lines to the left and to the right. And once we cannot remove this line anymore, let's say, we don't need to go further to the left. We only need to go until the lines that we check currently cannot be removed, and then we stop there, right? So this might look expensive, but it only takes as much as how many lines you remove, right? So, and then that becomes amortized logarithmic time. The logarithmic comes from the binary search and the set, right? Yeah, so yeah, basically, but the data structure, even though some insertion might take a lot of time, but if that lot of time comes from deleting the previous operations, that's fine. That's the amortized constant, or in this case, logarithmic, because that's binary search, right? Okay. So yeah, amortized means, yeah, you know, in average. So if you do n operations, the sum at most is n of n, so the average is just divided by n of n. This is n of n. Even though some operations might be expensive, but the average is still okay. Any question? Yeah, I won't show the code for this, but yeah, you can imagine, right? You just change the factor that you set, it's for your exercise. Yeah, so just you set binary search using load bound, and then, oh yeah, be careful if you use set S, do not do lower bound S. How many of you have done this before? Yeah. This will be for n.
How do you query?
How do you?
How do you query by x position?
Oh, yeah. Basically, yeah. Okay. This code is not enough actually. This code is not enough. You need to also have a factor of where the x times is here, and then when you at the end of this loop, you check whether the line size is greater than 1. If it is, then yeah. So yeah, here in this, you do something like if lines dot size greater than 1, you do like x dot push back the intersection point of lines top and top the second top, something like that, right? And then when you do pop back, you also x dot pull back. That will give you the list of the middle point. It will have one less element with the lines because you assume the these lines are unbounded. And then let's say that these lines you will have the x of this. Something like that, yeah.
The same thing for the dynamic version.
The dynamic you just finally search the gradient.
But what if I want to like ask for like if I have an actual query?
Oh yeah. The query you do this. Okay. But because the line that is inserted, you don't have an x, you have a gradient. You binary search on the lines to find where the gradient should be in between. I'm going to say there's this, and then there's a line that has this gradient. You binary search to find this between these two.
Okay.
Yeah. Okay, sorry, coming back to set. You should do as the lower bound instead. Yeah. So this is a lower bound that is provided by the STD set instead of using input algorithms, because that will just see the it won't basically know that it's a set that you can traverse the binary search tree, but it will do stupid method like it will increase one by one, like find the like a binary search on an array. It finds the middle point and then it can be one. Because STD set is not randomized access iterator. So yeah, in a factor, because it's randomized access, you can access any elements you want, like the third value or the fifth value. If you do lower bound feed or begin feed of n, it will give you log n. But in a set, it will actually flatten out the things first, becomes randomized access, and that takes log n. Yeah, so if you want to binary search on a set, you do this. This will do the reversal of the binary search tree properly. Okay, yeah, I hope you already know that. So yeah, even if you already know that, some of us still make that mistake. I also did it a couple of times. Yeah, you got PRE and then failed system test. Okay. Yeah. So any other question? Okay. So yeah. Okay. This is example problem. You go to this. You go to this as well. Okay. So yeah. That's for professional. Next, yeah, again I talk about Shifa and Compare.
I have a question. We normally use Lichau tree to like do the dynamic convexal tree. How does it compare with the set implementation?
I actually haven't learned that a lot, but yeah, usually if you want to solve some task that can be solved using fully dynamic variant of this, you can use Lichau tree as well. I haven't done like rough analysis of that and how does the complexity compare. But if you know that stuff, you're probably fine not learning this. You can solve most tasks using that. Yes. Okay, next. Define compare optimization on dynamic programming. This is actually newer stuff. Like convex hull trick has been around longer, I think, because you can see the task has been there from 2010, or even you can even find earlier tasks as well. But this is newer, still pretty old, but newer than convex hull. So yeah, let's say the common DP as before, like you want to find where the cutting point or something like that, and Okay, and let's say, yeah, this is usually useful when the value of the DP, the previous DP, we already got from 1 to n. Okay, so we have already like DP I minus 1, let's say, and we want to compute a new one, right? Because, yeah, usually this problem is like, you want to make k partitions or something like that, and this is usually like how many partitions you have made so far, right? So, yeah, because we're going to fill this DP value not in increasing order. So if we rely on the previous value, then this might not work. So usually this DP is good when the value of another DP that we require or already have a full from 1 to n, something like that. You get what I mean, right? Okay. So yeah, let's say DPij is finding the k where I minus 1k plus some function cost, right? And let's say this j has this cost. This cost has a property where the optimum point. So let's say we want to find the dp of this, right? Let's say the minimum is here. So this plus some cost to go from here to here, right? And let's say the optimum from this is not smaller than that, right? So let's say the cost function has this constraint, right? So so yeah, if that is the constraint, then when we want to find this dp, instead of n squared using the previous method, we can do it in n log n, right? Yeah, you might think that, oh, because the optimum value of this is not smaller than this, then you can just look from here to there. It's still n squared. The worst case, if it was the optimum is all actually on the front, and then the next you still have to check to the end again, but it's actually the front again, and then, yeah, you get the idea, right? So if you optimize your loop to go from the previous optimum position to n, it's still n squared, right? On the worst case. On average case, maybe if the optimum of here is already here, then the rest is just a small loop. But in the worst case, it still can be n squared. Okay. But actually, there's a method to do it in n log n, and yeah, basically the idea is that we actually try to find what's the dp of this value first in the middle, and then if let's say, and we do it naively, we do looping from 1 to n on the previous dp that we refer to, right? And again, this is why we need the previous dp to be computed fully first, because again we want to calculate this by doing a nice steps when the rest is not filled yet. Okay, so yeah, we can find the optimum position for this, and then we try to fill the rest by only, let's say the optimum is here. So when we try to solve this, we only look on this part, and when we want to solve this, we only look at this part. So that's the idea, right? So here is the code. So yeah, basically, yeah, DNC, define conquer, and R is which R is in this dimension, and OPTL and OPTR is in this dimension. So yeah, L and R is which dp values we want to compute, and OPTL and OPTR is we already know the optimum positions for this range twice within this range, right? So yeah, so the best case, if it's the index is we don't need to compute anything anymore, we just return. Otherwise, take the middle and then do the naive operation on the middle. Okay, and then yeah, find the optimum, and then when we want to solve this, we can use OPTL but stop at OPT, right? Okay. Okay. Yeah, and this becomes n log n because each layer, right, let's say, so the first layer we want to calculate dpm, we need om, right? That's fine. Second layer, for solving this, we want to find this m, right? We need to look this, and for this m, we need to look this, right? But the total is still om. So in each layer, even though it's there are more m's to calculate, but the sum of the loop taken for these ends are ON. Right? So, and there are log n layers because this, even though the OPT might be divided weirdly, like it can be the OPT is here and then the next layer, the OPT is unbalanced. But we know that the divide and conquer on this is balanced. We always take the middle, and then the rest is always like this, even though the optimum might be something like this, right? But we know that this is always divided nicely, and that means we always have log n layers, right? And total is n log. Any question? Yeah. Okay. But yeah, again, we need to make sure that this property is satisfied. Yeah. Because you can see why. It's not that you assume that the OPT of here is here, but it's actually here, and you only look here, and then it becomes wrong answer. Right. So yeah. Okay. Yeah. Okay. Example. So this problem where you can later solve if you want. If you want to exercise this define conquer technique. So this problem, let's say you are given n mines, and by mines is the way you can dig for gold, not like balls. Okay. They're gold or mine. So you're given n mines, and you are given the position of each mine, right? Xi, and the x is increasing, so like from left to right. And then each mine contains some number of gold, right? And then, so we want to gather this gold into only k points, k mines, right? And then, yeah, we need to move the gold so that it's only located on k different mines. And then moving gold, there's a cost. If you want to move the gold from I to j, it takes xi minus xj cost, right? And then we want to find what's the minimum cost. That's the constraint. So yeah.
That's the cost of moving 1 unit of gold?
Yes, 1 unit of gold, not Wi unit of gold. Yes. So yeah, how do you solve it? The value of Wi can be large, can be 20 minus 29. X also. So the value of X also can be high. Yeah.
You basically need to make organizing range, right?
Uh-huh.
So it's just going the also one range. Maybe the DP at a certain point, given that you already put so many ranges, is how long the range is. Right?
So sorry, what's the DP again?
It's two-dimensional DP.
Okay.
You're standing at point I, so you're looking at certain prefix.
Okay.
You want to put k ranges.
Okay.
What the starting point of the last range is.
Okay.
And that, I think, has that property that you need to that.
Okay. But how do you like the range, and then when you get j, like say I and then k, and then you want to find j, how do you find the cost to group I and j together? I and j together? No, my question is, let's say you want to partition this. This is, let's say, dpik. So you want, and this is the I prefix, is 1 to I. And then you're saying you want to look where's the j, so that we want to group this together, right? How do you compute the cost of grouping this together? But the W is different.
The prefix where half the gold is split. So if you have a range, you take the prefix where half the gold is, and that
Half the gold, right? Yeah. So you need to take care of the W as well. Yeah. Okay. Yeah. So yeah, if you like a weighted medium, basically. But yeah, that is fine. Yeah, that's correct. Yeah, and then yeah, because I just told you about DNC, so you know that it satisfies the property. Normally you need to prove it, but yeah, in this case it actually works. Yeah, so yeah, I guess it's standard, right? DP, the remaining number of groups that you can make, and then I is okay. In this case I use suffix. And then yeah, we want to j greater than I, but this is kn square, and then we can find for a fixed value of remaining, we can find the whole table in m of n. Yeah, and this actually the cost function satisfies that. Yeah, proof by contradiction. Yeah, let's say yeah, let's say this is dp rem, and then let's say this is I, and let's say this is I plus 1, and let's say the OPP does not match what we expected, so let's say the OPP is J. Sorry, the other way around. Yeah, let's say OPP I is K and OPP I plus 1 is J, where J is smaller than K, right? And we know that the DP value of this this is this extent. Yeah, okay. Let's say DP rem I is we only care about the physics, not the suffix. Sorry. Yeah, so yeah, we know that dpi cannot be larger than dpi plus 1, right? Because more elements means you need more cost, right? Definitely. Might be the same, but not smaller. Yeah, and we know that dpi is cos ik plus dpk plus 1 because that's the definition of OPT there. Okay, so you can just expand what dp means. Yeah, and then yeah, and this dp is dp from the previous remaining value. This dp and this dp is dp from the previous remaining value. Yeah, and this slide is a bit confusing. Wait, what's the previous slide there? I think it's 30 something. 27. I need to fix that 65 as well. Okay, and then yeah, we know dpi is smaller than dpi plus 1, and we know that oppi plus 1 is j, which means because j is some of these things that we got. But yeah, the idea is that because the OPTOs, one of them is j, then we know that, oh yeah, correct. Because OPTI plus 1 is j, we know that taking this value is smaller than taking this value, right? So OPTI plus 1, cos I plus 1 to j plus this is not more optimal basically. Because if this is more optimal, then OPTI plus 1 becomes j, right? And then you combine these two together. Yeah, this part is the same, right? And then you got this. You got. Sorry, no. This part is the same one, right? And this is the same. So this part is smaller than this, right? Yeah. But that means we can cancel out this, and we got cos ik is smaller than cos I plus 1k, which cannot be, right? The cost from the cost of gathering these mines must be more expensive than gathering these 2 mines, right? So yeah, it can't be. So yeah, basically that's the proof. It's usually some math works. Yeah, usually some in CP you can trust your instincts, but if you get wrong answer, then you probably need to figure out why it's wrong answer. It can be because your code is bugged or because this is not true. So you try to figure out whether this property is actually satisfied, and if you can prove it, then you can focus on your code to try find your mistake. Okay. Yeah, I'll fix this slide so it's less confusing. Okay, so now becomes k times m log n. Okay, Another different conquer task. This might not be DP, but the technique is similar. Not very similar.
One question about
Sorry?
last problem.
Sorry.
The bounds were like 5,000 and 5,000. And what was the time limit? Because an extra log might be slow.
I forgot what's the timing, but this is the intended solution.
Okay.
Yeah. It's from this context. Yeah. Okay. Yeah. Okay. Another different conquer task. We're going to look at this problem. Question 1, problem C. Some of you might have visual too. Yeah, so the problem is given n people in a line is having a color. For each k, we want to partition the people so that each group is contiguous and they are wearing at most k distinct colors. Visual too, right? Yeah. So n is one. Right? So yeah, I think maybe mentioned yesterday we can use persistent segment tree. But yeah, that's complicated. You need the persistent segment tree, you need the binary search, harmonic series R, right? And at the end when we discuss this stuff, I mentioned briefly that we can use different concepts, right? And yeah, funny story. So no, maybe not so funny. So this task I actually planned to use for today's context, and when I looked through my tasks yesterday, I forgot to take a look at today's context, and it turns out that this task is actually used for today. So last night I removed this task from today's context and changed it to something else. Okay, but yeah, because this task can also be solved with divide and conquer. Yeah, that's why I plan to use this task for today. So yeah, any of you want? Okay, maybe I give some time for you to figure out the divide and conquer system. So yeah, remember yesterday we find a persistent segment tree solution with this complexity, right? Or maybe log cube. Log cube? No, log square, I think. Log square, because we can remove the binary sum. Yeah. The divide and conquer solution might not be cheaper than this, but it's much shorter to work. We don't need complicated data structure. Yeah.
Like updates, right? To like contain like the current query that goes from L to R, and then you move the pointers to update for the next query. Is some result of it.
Okay. This is still using the. So for each k you find, for each L you try to find the R to find the R. Is that? What is the query here? Like the L and R is like how many distinct colors you get?
Yeah, you want to query for how many distinct elements there are. You want to take the current query like a set or something. And then if you as for the next query, you just move the pointers.
But we need these queries to be online because if you use binary search, then we have to answer something. Yeah, but if you use more, you cannot do all this.
Similar to how we use the component node, in the sense that it's taking the pointers from the current queries L and R, and we just move them to the next query and removing elements from left to right.
But then would the binary search become n? Because like when you say you want to find this L, and then let's say we have a fixed value of k that we want to solve, and we want to find the largest index such that there is still less than k distinct colors, less than k plus one distinct colors. Then let's say this is L, this is M. We want the binary search here M, and then let's say we already have the answer for this. But if you do like more like, then we have to increase one by one, right? This. And that becomes ON per case.
You don't do binary search, you just normal divide and conquer.
How do you do divide and conquer? Like, okay, so we want to solve a fixed k, right? Solve a fixed value of k. And then yesterday we discussed that we can do this greedily. So 1, let's say, we want to find what's the furthest index we can make such that, let's say this is, such that this is still less than k distinct color, right? But how do you find this? How do you find this index? Because if you look through, it can be ON.
Can we find that index like binary searching?
Sorry? We find?
Couldn't we find that index like binary searching?
Okay.
With yeah, even with a multiset or with just counting how much of each color we have.
Yeah, but yesterday we discussed that if you binary search, then we have to be able to count how many distinct colors in here, and we use persistent segment tree for that. No? Yeah, but we want another solution.
I think you can keep a sliding window when you are like inside the divide and conquer to count the number of distinct colors.
So you divide and conquer the k, okay? So you try to find if k is n over n first, is that what you want?
Yeah, exactly.
Okay.
Yeah. Then you break like on a half, and
this thing you break into half. The array.
yeah,
The array you break into half. Okay. Okay.
like the window. Like let me think more on the
Okay.
idea.
Yep.
So the problem, like the problem of that's what worries about so many distinct colors or distinct integers in an array.
Mm-hmm.
So you can use a persistent segment tree.
Yeah, we want to avoid persistent segment tree.
What?
We want to avoid using persistent segment tree in this. Yeah. Yeah.
You can use another thing about arbitrarily, like starting at a point, you want to know what's the maximum array that you can go to, right? Maintaining at most 3 different colors.
So you start from the middle, yeah?
Yeah, you start from the middle and you calculate that linearly,
Okay.
and then you split into 2 arrays, and each of the 2 arrays you have less candidates, right?
But this partition might not be optimal, right? Like this partition in the middle might not be optimal. Let's say k is 2, and then
No, what I mean is for each item in the array, you calculate what's the maximum range
I see.
in that point.
Okay.
Has the most k colors, and then after you calculate all that, you do the you start in the initial element, then you jump that many items, and then you jump that many items.
But that is n squared, no? Because that's m of n for a single value of k, right? Yeah. Yep.
Can you do something incremental? I mean, you begin from k1 equal 1,
Okay.
and in each step, for each iteration,
and go at a set of the different integrals, and instead you only update with the ones that you need. I mean, you only will update at most n over k, n over elements.
Yeah, but that still takes OM per k, right? Because for k, for a fixed value of k, even though the value of k can be large, can be like, let's say n over 2, you know that the answer is at most 2, the maximum partition can be at most 2, but it still takes OM to find out what's the exact number, right? Yeah, so that still takes OM for every fixed value of k. So if we do a linear loop for each k, for each value of k, then you will need ON per k, because even though the answer is small, if the k is large, but you still need ON if you do linear loop.
Yeah, but again, you say keeping the data for case before.
Okay, but that might not help, because let's say this is k is 2. Let's say that for k is 2, we split first here, right? So you can start a new partition here. You might also compute what's the furthest you can make if k is 3, but for k is 3, you might actually not start at this point. So you need to redo the search again. Right? Yeah? Oh, actually for k is 3, the start will be more to the right, but you get the idea. Like, yeah, you need to do the result.
So if I have some, let's say for every position in the array, I know the longest I can go using k colors.
Okay?
Now let's try to compute with k plus 1.
Okay?
I know that at the end of the k range, the next one is a different color, because otherwise I would just have got it as well.
Right?
So can I use the k equals 1 to extend it?
Yeah, but again, the start position might not be the same, right? So the k2, you might need to start from here. This is the cut, but for k3, you might go all the way here, and then you need to compute from here and split from here.
What if we do the divide and conquer over the k?
Okay? And then?
Like, I don't have the complete idea, but maybe instead of trying to split where we fall over the initial position, try to calculate for each position for n over 2, and then going over n over 4. Maybe that's the number of positions we need to consider. The number of n positions we need to consider might go down, but I'm not sure if we can use that for anything.
Okay.
I think that might be.
Interesting thought. So yeah, I guess some hints. You know that for k, the graph will decrease, right? This is k plus 1 will decrease, the answer. This is answer. This is k. Right? So this is one observation. And then we know that how many distinct values can be in the answer?
N over k?
Without k. How many distinct answers? So this can? What?
The total is, the sum will be...
No, not the sum. Distinct values. Like some of this will be the same, right? Like that, and then
Square root?
square root of n. Why?
Because the first square root values for k can be distinct, and the last have to be less than square root.
Okay, yeah. So 2 square root, right?
Yeah.
At most, yeah. Okay, so what can you take advantage of that? How can you take advantage of that?
Can you explain why you square root?
Because for the first, for k greater than square root, n over k is smaller than square root. Right, so there can be only the square root less than square root and distinct values. Right, and then the first is, yeah, there can be a square root distinct values as well. So total is 2 square root distinct values. Right.
Okay.
Yeah, we know that the answer can be at most n over k, right? We talked about yesterday as well. Yeah. Yeah.
I think you can start, for example, with k equals n over 2
Okay.
and compute it linearly.
Okay.
And then you go to the 2 to like 1/4 n to n over 4 and
Yep.
n over 4 and compute it.
Yep.
And once you have two adjacent values that are the same,
Yep.
you don't compute the part.
Yes, exactly. Yes. This is the line of circle. And that naive is 10 lines maybe using SAT to, yeah, you can get naively, right? Yeah. Maybe n log n if you use SAT, but you can do it linearly as well using a fast SAT or something. This is the line of circle. Yeah, basically, compute k equals n over 2. That's the defined formula. Yeah, so if, and then you do left and right. If both the endpoints have the same value, then you know that the middle have the same value as well. That's what we see.
Can you repeat, please?
So yeah, basically this is the code. Basically, you solve. This is now k. So you find the value of what's k4 naively, or in ON, right? And then you try to solve this and this. Okay, first you get k1 and k8 as well, naively as well, these two, right? And then if these two are the same, you know that all of this is the same as this and this, right? Yeah.
And for a fixed k, you do it grid?
ON, ON. Yeah. So now if that for a fixed k, if the answer on the left and right boundary is the same, you just take the values because you know that it's a decreasing function, so it must be the same all in the middle, right? Otherwise, you do it naively in ON here. And this at most, it's something n square root, and the analysis is a bit complicated, but yeah, it's actually, well, we know that it's not faster than this because this naive made for each of the distinct values of naive, it's at least called once or even twice maybe. Yeah. But yeah, once so it at least this, but yeah, it turns out that this is also the upper bound. So I think this plus log n, something like that. Yeah, and because we do the define conquer, if there is a long chain of same values, we only can query this at most, I don't know, some constant number of times because of the define conquer. Let's actually make log n. But yeah, it's small because we do it this way. Yeah, and the code is very short. The distinct values?
Yeah.
The distinct values? Okay. Yeah. So for k greater than square root of n, we know that the answer is not more than kn over k, right? Yeah. So it's smaller than square root. So yeah, this for k greater than square root, there can be only square root n distinct values, and then the beginning also there was square root n distinct values. Yeah. Yeah, this is a sample on this problem. You can try it later. This task using this solution. Very short. The complexity is more expensive actually, but very short. And yeah, this basically also works even if the naive, yeah, basically for more generic problem where the naive methods might not be this, but still the property that we need to satisfy is that the function are decreasing and the distinct values are small. So if that satisfies, we can use this technique. If the function decreases or increases, basically monotonic, and then the number of distinct values is small, we can do this. Yeah?
For that calculation, how do you use something like a log of columns, or is it a general log like if you're looking at an array, using that sort of like
Yeah.
because the trivial bound would be n start of n times log of n.
Yeah, maybe that's the case. I don't know, but yeah, I don't know what's the real complexity here. It's either this or this, but it passes the time here. Yeah, n square root of n times log n might be tight, but it still passes.
It's close, right? Because if you have answer for both endpoints, if the answer for the middle value is different from then you increase the number of distinct elements. Otherwise, half of your array you have the answer for free. So each iteration we either increase the number of distinct elements or we throw away half the array.
I don't really get what you're saying. So why it increases the number of distinct elements?
Because you have the answer for left and right. We have like 1 and 10. If the answer for the middle like 5, then we have one more distinct answer, right? If it's either 1 or 10, then half the array we have the answer for 3. So we either half the number of half the array, or we increase the number of distinct.
Oh, okay. So what you're saying is that, I see what you're saying. So you're saying that this should be plus then?
Plus,
Yeah. Oh yeah, that makes sense actually. Yeah. So you either not increase, right? I mean, like there are several costs, and the cost can be from this and this, right? And then yeah, so each trying to solve every time you go unsmith, it's either reducing the number of distinct elements or no. But I mean, but like even though there's a contiguous set of same values, you can take some amount of cost to compute this, because like you can be unlucky, instead of finding this first, you can be unlucky, like something like that.
When you find the cutoff point, you're recursing, you compute this one, and they're different. To find where it cuts off, you implicitly does binary search, so it does it all the time. It computes the same value enough times until it finds.
But the problem here is that if there is a long sequence of k with the same answer,
yes,
we might take some amount of time to, instead of just if we query both endpoints first, then that's nice, because the rest we just not calculate.
Yeah, that's what I'm saying. Yes. So suppose we have k and k plus 1. At some point it changes.
Right.
The only way to know is computing the naive a bunch of times.
Right. So does that make it plus or
I
times?
think it's times.
Times.
Because you compute for each different answer, you compute it
At most log n times.
times.
Yeah. Yeah, it's probably times. Yeah.
And
Because
you can divide it into a segment and then boost log different logs.
right. So if there's a continuous segment, you at most query this log n times, right? By query, I mean do naively for this. Like you might miss, like you might need to query naively on some of these points, but this is at most log n times, right? Yeah. So it's probably this, but I don't know. Yeah. It's definitely not more than this, and definitely not less than this. Not sure whether it's actually which one, or whether it's something actually in between. Maybe it's like square root of n times inverse Ackermann function. You know? But yeah, again, we can use this for more generic, where the distinct values. So basically, we use this, it becomes n times log n times the number of distinct values in the number of distinct values basically. So if the number of distinct values is small and the function is monotonic, we can use this. This is the complexity. And yeah, the code is much shorter than persistent, or even on some problems, if you can't solve the naive method faster than ON, then yeah, you have to use this. Okay.
I think we can do a binary search too, and then the complexity will be n times start with n times log. Like starting from one, the same problem. Starting from one, you're gonna binary search to see till which k the answer is equal to one. So you do at most log times
Yeah, you can do that. So basically, yeah. So you find where the basically like from here, because we know it's 1, we vary results until that point is 1, and then we query this naively, and then we vary results until which point it's this value, right?
Yes.
Yeah, but yeah, the same complexity, right? So yeah. Okay. So last technique, last optimization. Before that, any questions so far? Okay. So last one is this node scale optimization. Again, some of you have probably seen, but let's go through it. So now let's say the DP is now a 2-dimension where usually it's from I to J kind of thing, like substring of like an interval DP. So now, yeah, we try to find where the best position to cut ij, like let's say it's at k, and then we compute, there's a sum cost, and then we compute the left half of the partition and the right half of the partition. Right, so this is what we can solve it now, and oh yeah, and then this is the another condition that needs to be satisfied in order to use the node optimization. So the OPT of ij must be between OPT ij minus 1 and OPT I plus 1j. Right? Yeah, so yeah, I guess it's quite obvious now how to optimize this. Basically, we make sure to compute the dp from the greatest value of I first, and then among the same I we compute from the lowest j. So basically build the dp from bottom to top, left to right, something like that. So whenever we want to compute the dpij, we already have dpij minus 1 and dpi plus 1j. And if we also maintain where's the optimal cutting point for each dp, we just look between these two values, right? And this constraint might be too restricting, like what kind of problem has this property, but I'll show you later what's the condition of the cost such that this is optimal, this is true, right? Yeah, so it's obvious that the loop can be optimized. What's the total running time? So yeah, let's say this is I, this is J, and let's say each of these cell is the value of OPT ij. So this cell is OPT 5, 6, let's say, right? And then to compute this, we only look from OPT this to OPT this, right? OPT ij minus 1 to OPT I plus 1j. And yeah, basically this means the time complexity to compute this dp is this OPT minus this OPT, right? And then you can see the arrows, we can cancel out all values, many values, right? So to compute this takes this minus this, to compute this takes this minus this, so this can actually be cancelled out, right? And yeah, you can see that this basically just the sum of this OPT minus the sum of that OPT, and plus that. No, there's OPT. Yeah, OPT 1.5 is useless. So yeah, basically just the sum of this OPT minus the sum of that OPT. Right, and yeah, and because there's at most, we need to sum at most m OPTs values, and each OPT value can be, of course, between 1 to n, it's n squared. Right? Basically, DPI populating the table now is as big as the size of the table, so it's basically for price constant. Right. So yeah, and then yeah, the cost if it's if it's increasing when you increase the size of the table, no, sorry, when you, yeah, basically, yeah, the cost if you compute this dp and if you compute this dp, if this cost is higher than this, let's say the simplest one is, let's say if it's just the sum, if the cost is just the sum of I and j. So let's say the problem is something like you want to partition this, but each time you partition, you take the cost of what's the sum of the thing that you want to partition. So this you partition here, this you partition here, right? So this kind of cost, where the cost is just the sum of the elements that is currently in your dp, satisfies this, right? So the cost of ij is smaller than that, and the cost of this plus this is greater than this plus this. This plus this greater than or equal to this plus this. Right, so more elements is more expensive. So yeah, so just now the sum of x is still fine, but if it's the square root sum of x, let's say cos ij is square root sum of x, then this is not true anymore, because usually with square root, if you have many elements together, it's usually smaller, like they increases slower than linear. Right, so yeah, if it's sum, this is actually the same thing. Right, if the cost function is the sum, this is actually equal, which is fine. Yeah, so if these two conditions met, and if this is met, then it's true for brother as well. So if this is, you know that if this is I, let's say j k l, we know that cos I l plus cos j k is greater than cos I k plus cos j l. Yeah, I think this is called quadrangularity and inequality, something like that. Yeah. Basically, the cost, yeah, again, the cost has to something like grows faster than linear. Like if you have more elements, it's more expensive. Something like faster than linear. This plus this is greater than this plus this. Okay. Yeah, the proof of this, like this implies this, is messy. Is, yeah, you can work it out yourself or Google it. Yeah. But basically, yeah, very messy. Just now we already have this messy proof, right? It's even more messier than this. So I don't want to discuss now. Yeah. Yeah. Oh yeah, this is what I mentioned earlier. So because that is one of the conditions, this means we can solve this. We can use node yaw when the cost function is grows faster than linear. Okay. Yeah. So the classic usage of this technique of this node yaw optimization is a optimal binary search tree problem. Basically, what I just mentioned just now is basically called optimal binary search tree problem. So yeah, optimal binary search tree problem is given n elements, and we know that we want to construct a binary search tree from this element, and we know that each element, how many times they are going to be called. Yeah, we want to construct the binary search tree, right? So yeah, so basically, let's say these elements are sorted, right? And then let's say this is going to be called 10 times, 20 times, 10 times, 5 times, 2 times, 10 times, 7 times, right? So the optimal here might be put the root 5 here because it's called less times, but I don't know, like maybe. But yeah, basically every time you put a root here, the rest of the elements will be called once more depth, right? So okay, let's just put an example. Let's say this is the binary search tree that we construct. So the cost of this binary search tree will be 5 is 2. This is 2 times, so 2 times 1 plus 10 times 2, 7 times 2, 3 will be called 10 times 3, and so on, right? Because yeah, if you put a node deep down in the binary search tree, sorry, the root should be 2 then. My mistake. The root should be the one that has more number of times called. Right, but yeah, you get the idea, right? So yeah, the more deep they are, it will be, each call will be more expensive, right? So yeah, this basically you can, is basically this, and the cost is just the sum, because every time you make a partition, let's say, and when partition I mean choose a node as a root, then you must put this on the left side of this, right? 1, 2, 3, and the cost is you can sum this up, because yeah, 5, 10 plus 20, because the rest of these elements will take a cost, right? And then 1, 2, 3. Let's say you take 2 here, and then this will, you can sum this 40 plus dp1, 1, dp3, 3, right? Yeah. Yeah. So this optimal binary search tree problem is basically this, and the cost is just the sum of the ei there, right? So yeah. So this is the most. I think it's even in the original paper, like by Nus and Yao, probably. Yeah. Like in the original paper, when they talk about this optimization, they use this problem to illustrate how their algorithm can be used to calculate dp faster. Because otherwise it's O n cube, right? Each dp you need to look from I to j, then that's n cube. Okay, any question? Okay, so that's all the DP optimizations that we're going to talk about. The rest is just lots of task example, because finding DP task is easier than finding persistent segment DP task. Yeah, but we're going to take a break, maybe like 20 minutes, 30 minutes. I won't say it's 10 minutes, but it's never 10 minutes. Yeah, and when we come back, we're going to see some examples where we can use either of the DP optimizations to solve. So yeah, let's take a break.
Te escribo un programita, 4 líneas.
Okay, let's. Okay, let's continue. Okay, so as I mentioned before the break, we're going to discuss, we're going to just do some tasks from here using some of the techniques we just saw. So yeah, so we're going in increasing difficulty, I hope, at least from my perspective. Okay, so first of all, this is still a standard technique actually, but a standard task, but we're going to take a look. And yeah, again, if you want to solve this later, you can go to this task. So the problem is that we have n rectangular plots with width and height. Yeah, we can we want to cover all of these rectangular plots by buying some lands, and if we group some rectangles together, we need to buy a land that cover enough of the height and the weight, and for each land, the cost is the area of the land, right? And yeah, we want to find the minimum total cost, the total for, because we have several lands, we want to take the total of the cost, right? And yeah, and it's 50,000, and the height and the width can be lot. So how do we solve this? Yep.
If there's a plot of land which is smaller than the other plot, then
What do you mean by strictly smaller?
have less width on the left side.
Okay. Okay.
You can keep only a sequence of plots that are decreasing in width, increasing in height.
Okay.
Right?
Yep.
And it's always optimal to cover like a subarray of those.
And then it's n square, right? It's not enough.
You do connect the person.
Okay.
When if you click I and J, the process is going to be the height of I times the width of J and plus the dp of J minus 1. Right?
Okay.
So you just apply kind of converting this.
Okay. How do you eliminate the strictly smaller plot? How do you remove the plots that is strictly smaller than another plot? Sorry?
Well, the next step. Right? You like you sort everybody by width or by height or whatever, and you do a stick hash where you eliminate the element on top of the stack. Like if you sort by width, by increasing width, if you are in an element and you see that the element on the top of the stack is has less height than the current one, you just stop it. Right?
Yeah. Okay. Yeah. So okay, let's just go through this quickly. So yeah, basically, yeah, they mentioned all the required techniques here, required points here. That first we, because if there is a rectangular that has smaller width and weight, then we can just ignore this, because whichever this rectangle we group to, we can also group this in the same way, and that won't change the land area. So yeah, we can ignore that, and the way we ignore that is that we sort. Let's say this is the height. If we sort this, like let's say something like that, then this should be decreasing, because if this is increasing, let's say, then this is not required. So yeah, the way we can remove this is we use a stack. So yeah, let's say, yeah, so here we process this way, 1, 10, 3, 4, so we push 10 into the stack, 4 into the stack, But now 6 is actually greater than 4, so we actually pop this and remove this as well. 6, 7, the same thing, we remove this, 7, yeah. And we can actually pop this multiple times, right? If this is 8, this is 7, and this is 9. Then when you want to put 9, you remove these 2, right? Yeah. So now you have, so you pop the element from the stack until the top of the stack is higher than this value. So now you have a clean set of increasing height and decreasing weight. So this is increasing, this is decreasing. Yeah, once you have that, let's say this is the height, this is the weight. Yeah, we can do dp with convex out, where if we want to solve this, let's say dpi is the minimum. Let's say I is the suffix, let's say, so this, let's say dp3 is only considering that. Minimum of I, j, n, dpj plus 1. And then, yeah, because we already sorted this nice way, we know that when we, let's say this is I, when we want to cut here, we know the area is just this times this, right? The maximum height times the maximum weight. So h, j, wi plus, no, there's no plus. Yeah. And then again, yeah, we know that, again, we can say this is the C, and this is the M, or HDP. And then this is the X, right? So, yeah, we can solve this in n log n, I think. Or maybe linear again, like commando, I do. Yeah, depending whether this is increasing or not. Maybe it is. I don't know. But yeah, 50k you can do n log n. But for log n, yeah, but yeah, that's the solution for this problem. Okay? Should be not so hard. Okay. Yeah, and of course you process from dpn, dpn n minus 1, dpn minus 2, and then while doing that you put the dp on the line, right, on the mirror. Okay, next is this problem from the right. So the problem is, any questions?
Sorry. Just 1 second to process.
Oh.
Yes.
Okay, yep. Yeah, basically, when you finish computing dpi, insert a line with the h and the dp. This is the m, this is the c, and then this means you can just query using wi as the x. Okay. So next. Yeah. So you are guessing a number x between 1 to n integers, and for every guess you can give p and q, and yeah, that's the range of the p and q that it must be. So must be between 0 and n, and p must be not greater than q. And for every guess, you are told whether so there are 3 ranges, right? From 1 to p, or p to q, or q to n, right? Yeah. You are told which one, and but you need to pay respectively, right? So a, b, c is given, and n is given. So the input is just n, a, b, c. Yeah, find the minimum cost to guess the number, right? So for example, let's say a, b, c is just 1, right? Then the answer is just something like ceiling to the log 3 of n, right? Because your guesses can be just always divide the number into 3, and whichever you are told, you do that again, right? So if a and b and c is 1, you do this, right? But let's say if a is infinitely large and b and c is 1, then the answer becomes log n, right? Yeah, you don't want the number to be on the left of your query, right? So you always do p equals 0 or something like that, right? So yeah, so this is some example inputs, or more complicated one is n is 10, a is 1, b is 2, c is 3. The answer is 5. This is how you query, right? And this 3 covers all the possibilities, and whatever. So this is your p and q is your strategy, and whatever happens, you will always not pay more than 5. Right? So how do you solve it?
In the previous slide, it was x. It should be x is bigger than q, right?
That should be Q smaller than X. Yes. Yeah. This should be Q smaller than X. Yeah. So yeah, the N can be very big. Yeah. So you cannot do DP on N. How do you solve it? Again, this should be Q smaller than X. And this is some of the examples. If all the cost is the same, then just query in the middle every time to divide by 3. If some of them is infinitely large, so make sure you never get that, and you only divide by 2. Then your answer becomes log n. But yeah, now A, B, C can be given, and can be given as well. What is the minimum cost to guess the number? So let's wait. Someone else want to? Do you want to answer or ask questions? Sorry? Okay, yeah, so let's wait. Sorry? The worst case. I think this example should help you to see that, yeah, this strategy covers all the possible cases. Yeah. Sorry? Okay, sure. Okay, maybe you. You first.
You can with DC
Okay.
for value I, you store the maximum size of an array that you can solve with cost I.
Okay.
Or most I.
Okay.
Then to compute the new value, you have to add that add the DP at that value minus A, that value minus B, that value minus C.
Okay.
Right?
Okay. But how?
And the total value is small because it's going to be logarithmic and
Yep. Okay. Yeah. So yeah. This is the thing with where you notice. Okay, there's a dpn solution of this. Maybe it's n cube or something like that. But if the n is small, then you can do standard dp where the dpi is just what's the minimum cost of computing I, and then yeah, you do like you do something like this, right? 1 I, and then a plus dpi plus maximum of a plus dpi plus b comma b plus dpj j minus I j k minus j what am I doing? That's just 2jk where kl, j plus k plus l is I, and then yeah, this is just j, k, comma c plus dpi. So if the problem is the other way around where the value of n is small but the value of a is large, this is the dp, right? because basically you want to find where is the optimal cutting point, right? And yeah, you take the worst case. So if it turns out that the number is on the left, then you pay A plus BPJ, right? But if it's on the middle, B plus BPJ, and you take the worst case, you take the maximum, right? But now the problem has very large n and a small ABC, right? So we need to reverse where we take the DPI as the maximum number, the range of the number we can guess by using cos I, right? And yeah, this is turns out just DPI minus A plus DPJ minus B plus I minus B, I minus C. Right? Of course, if I is less than A, you just do the remaining, right? Basically this is if A is larger than A, you do this, otherwise 0. If I is larger than B, you do this, otherwise 0. So you get the idea, right? And yeah, why you do this? Because yeah, basically if you have cost value I, then whatever you can guess with I minus A, you can like sort of append the thing, right? If you can have like, if you can guess 1 to 5 with I minus C, then you can basically this is how you query P and Q. Because if it turns out to be here, then you pay, then yeah, you need to pay C, so you have I minus C money remaining, something like that, right? So yeah, you just sum up these three numbers: DPI minus A plus DPI minus B plus DPI minus C. And yeah, the last piece of the analysis is that the answer can be small, because in the worst case, whatever the value of A and B and C can be, you can always do the log 3 method, and in the worst case, you'll get the maximum of ABC times log 3n. This is the maximum answer that it can be, so you just need to compute your BP value until this point, and then the last part is of course find the smallest I such that DPI is greater than. Right. Any question? Okay. Okay. Okay, next is again from APIO. It's I have mentioned APIO several times, but it's basically like the regional, the Asia version of IOI, like the regional version. Yeah, and because I'm in the Asia region, I know some tasks in this region that I can share with you. Yeah, so the question is about you are given array A of n elements, and you want to do this operation A times, where for each operation you cut the array, and then the cost of cutting that is the sum of the. So let's say you cut here, the sum of this times the sum of this, right? That's the cost. And then you want to do it 3 times so that the total cost is maximized. Okay. Yeah. So yeah, of course, when you cut here now, the cost becomes this times this. This is not counted in this cut. So yeah, once you already cut here, when you cut here, it's just this sum of this times sum of this. Oh yeah, of course. Of course, the split there might not be in the middle. You can split anywhere you want. So you can, yeah, of course you can split here. Sorry? Yeah, let's say, I don't think that's necessary condition, but let's say it's positive. It can be negative for some part, I think. Yeah, I think it also works. It's not positive. Okay.
Let's say you have the final solution, like this split ahead. We can say that the cost basically for each segment we get the sum of this guy here, and the sum of those outside, and it's the product of both. Because when you split, you are multiplying each other. Yeah.
But why it's not more optimal to cut in the middle first? Like you say, if this is the last one, you're saying that the cost is this times this, right? Sum?
For each segment.
And then this times this, yeah. But why it's not more optimal to cut in the middle first? So that it's this times this, and then you cut here this times this?
Oh, because the elements can vary.
Is what?
Because like the sum can vary, like each element can be different.
I didn't get it.
Like each element can be different because the elements in the array aren't the same. So you always split in the middle.
So you're saying because when you say this times this plus this times this, you're splitting from the left, yeah?
Yeah, it can be from the left.
Oh, okay. But you're saying that splitting in the middle, and then the cost becomes the sum of this times the sum of this is the same cost.
Yeah, it's the total cost.
The total cost is the same.
Yeah,
Okay,
it's
and
the
then?
total cost. So that's basically, let's say that's the sum of the segments x, okay? Like it is x times s is the total sum of the array minus x.
Okay.
So it would be x times s minus x squared.
Sorry, let me try. So sorry, okay? So if you cos this and the sum of this is s and this is x, so it becomes s minus x, right? And then, so this is sx minus x squared, and then?
And then you can use convex filtering because you can, like if you use a leaf child, you don't need to you can solve the problem with.
Okay, yeah. Okay, yeah, so, yeah, basically the first observation is here is that whatever the order of the cut, it actually doesn't matter. So yeah, if it matters, then this dp, you have to have two-dimensional dp, where it starts and where it ends, and when you cut here, the problem becomes dp from here to here and dp here to here. And you cut here, you have to calculate this dp, but with this problem actually where you cut doesn't matter, the order of the cut doesn't matter, so you can always pretend you are cutting from the left, right? And that's how you compute the cost, right? So yeah, this is just math works to figure out why it's not important. Yeah, basically, you can try small examples and see, oh, it doesn't really matter. So yeah, you just assume that it's true. So if this is A, B, C, you basically try to see why this is the same as this. This is the cost if you cut from the left, this is the cost if you cut from the right, and turns out they're the same. So just assume it works. Yeah, but then, yeah, you can see why it works. Basically, cutting whatever order you want is the same. The cost is the same. It's just the sum of the pairwise cost of the, like, if you cut like this is D, this is E. I mean, this is the sum of X is A, right? The cost will just be for each pairwise, it's the multiplication and then the sum. The cost will be like that. But yeah, okay. But anyway, so yeah, once you know this, we can do the dp we can cut from the left. So the dp now becomes standard like suffix dp. Like let's say dp ki is, if let's say we can make only consider the suffix I elements and we can make k more cuts, right? And the problem becomes finding the minimum j such that the sum of elements from I to j times the sum of elements from j plus 1 to n plus dp k minus 1j is minimum or maximum. Maximum. Yeah, because this is the cost of the cut and this is the remaining cost to make k minus 1 cuts, right? So yeah, as you mentioned, we can prefix sum this. And yeah, the good thing about this dp is now we don't need to do the trick or the dynamic convex or the convex sum online, because we know what's the value of dpk minus 1 first, and then we can solve the gradient on that dpk minus 1 first. So we don't need to do the dynamic variant, right? So yeah, basically this becomes prefix sum of j minus prefix sum of I minus 1 multiply by prefix sum of n minus prefix sum j, and then yeah, basically becomes prefix sum n, prefix sum j minus prefix sum pn pi minus 1. Yeah, you can figure out the rest, and some of this will be constant, some of this will depend on j, some of this can be factored out I and j, and then do the projection effect. So I'm just making sure it works, but yeah, it should be working. Yeah, so yeah, this is constant. No, not constant. It only depends on I, and then yeah, this is the part where the mx. So m is this, c is this, and then yeah, you vary with kmx. But yeah, if the function can grow like, because this is just a quadratic function, multiplication of two sum squared. If it grows like cube or fourth, and then this becomes I don't know, like this can be p. But yeah, if basically if you cannot factor out this into something that is just rely on I and something that just relies on j, it doesn't work. This thing doesn't work. So you have to factorize this thing into independent of I and independent of j. Okay, any questions? Okay, so Next is a problem from the further further 708 palindromic subsequence. So the question is, there is a string of n characters. For each I, calculate the number of palindromic subsequence containing ith character. And two subsequence considered different if there is an ith character that is chosen but not on the other subsequence, right? So even though the characters are the same, so let's say AA, then there are 4 palindromic subsequence, AA, and MD, right? So these two are considered different. And yeah, of course you multiply something, right? Okay. Yeah. How? For each I, calculate the number of polynomial subsequence containing the I character. Yeah, that's the question. And it's 3000.
Are the subsequence continuous?
No. So this is also palindromic subsequence. This A also counted.
If part time 26 doesn't
Used by characters, I mean Japanese characters that has thousands of characters. So yeah, you shouldn't rely on the set of characters being small. You want to answer? You want to answer? That's good.
So, I'll I'll say that the key of ij is the number of wait.
Okay, you go.
Okay, so a palindromic subsequence is like you take the first and the last character, they're the same, and the second and the second from the end is also the same, and so on. Right? That's a palindromic subsequence.
Oh yeah.
Okay. So now imagine you take the string, square, like square repeat, the string and the reverse of the string. Then two characters are the same. If you can put the string here, the reverse here, and mark all the positions where the two characters are the same. And then a palindromic substring would be like decreasing a sequence of marked squares that are decreasing in x and increasing in x and increasing in y.
Let's get an example.
You take all the pairs of positions that have the same character in the string, correct?
Sorry, I cannot find the. Oh. Okay, so let's say it's AAG. Okay, so let's say S is AAGA. I need to refer to projection. So you're saying this is reverse. So this is S, this is reverse of S. And then here you say it's the same, you mark it, right? And then what do you do again?
As the substring is a palindrome, if it's a sequence of marked squares, it is like this.
So let's say like what, sorry? Like
that the first square has to be somewhere, the next one has to be lower and to the right, and so on.
So something like this, maybe.
Yes.
Okay.
So that's not marked.
Sorry?
That square is not marked because it's A and B.
No.
Let's say A, B, A, very first. Yeah, okay.
That one is valid, and if you take the corresponding character, that's AA, right?
Okay, yeah.
And if you don't want them to overlap, you only have to look at the upper triangle.
Okay, so you only take a look at this.
No, not that triangle.
This.
Yes.
Okay.
It's a sequence of decreasing squares like this in that.
Sorry, do you take this one or this one? This one, you say.
Yeah.
Okay. So you want to find the number of subsequence that contains all marked characters and go like that.
Yes.
When is B choose here? Only B?
Only B, and that's exactly the diagonal. Right? That also has to be.
This? Oh, okay. So the upper triangle is like this.
Yes.
Okay, sorry.
So now you can calculate like a pair of indices ij, which is a point in that square. You can calculate how many subsequences there are that have those two indices, but like centered, right? So this part is the same as this part, and that's just the number of facts that end there, which can be calculated as the sum of prefixes. It's usually prefixes.
Wait, let me get right.
The way I imagine it is you take palindromic substring. You take the first and the last character. Those are three indices. Then take the second.
So let's say, sorry, let me interrupt. So let's say you have a palindromic subsequence, and the first one, and let's say this is A1, A2, A3, A4, A5. So this is, the A1 character, and this is A5 character. So you take the A1, A5 position in this cell, yeah? And then A2, A4, and then A3, A3, yeah. But why does it has to form a diagonal like that? Like why cannot I take this and this?
Yes, that
Oh, so it might do like this, but it,
yeah.
okay. I thought it has to be like this. Okay.
Yeah, it all has to be lower and to the right.
Okay, got it. But may have difference between the right and down. Might have different.
Yeah.
Okay. I thought it has to be the same. Sorry. Okay.
And counting the number of paths that end at a certain square, that can be done easily, like with a prefix and a 2D prefix and square.
Oh, I see. So basically from here you can 2D prefix sum this of the DP values, right? But you need online, right? No?
Yes, and you can do it online because you're constructing it in order. Right? Like suppose you do.
Oh, of course. Yeah. Okay. Okay. And then how do you answer for each I?
Okay, so that gives you the number for each pair.
Yep.
The number that like end in that pair line.
Yep.
That have
That like start and end at that index,
the
right?
middle is there.
Yep.
You need to compute how many you can put in the middle. Right?
Yep.
And that's the same DP but below. But reverse. Like you need to count the paths that go up and to the left and end that down. Right?
Okay, so basically your DP for each of this, you know how many parts you can make going down and going down.
Yes, and you multiply them. And that's the total number of paths that go through this.
If you multiply them, I guess. Yeah, okay. But how do you, because the question asks you to answer for each.
Yes.
Yeah, for each I.
And for each I you just add up in that row the numbers that.
Huh.
Each path on like mark square has one polynomial sequence, and you just want to count for each mark square how many paths go through it. But something like a length one path, right? That's one character polynomial sequence. Don't you like count those?
No, it's not one character.
It's either one or two.
Diagonal is one character.
Yeah.
If it's off the diagonal, it's two characters.
Yeah, if it's on this diagonal, I think it's one character, right? This diagonal is one character, but if your part is just containing this, then you basically choose the 2 and the 4. Yeah. Okay. I get the solution. And then you're saying that for the for I equals 4, you just sum up these numbers, yeah?
I think you need to consider the case where I is on the left and on the right of the top row.
Oh, and this as well.
Yeah.
Yeah. Okay. Basically, this is looping like the pair of I, right? Yeah. Like. Yeah, this works actually. Yep. Okay. Yeah. Looks good. Yeah. Yeah. Okay. Okay. This is good solution. Yeah. So this is the problem again. If you want to try to submit, but yeah, dealing with encoder is a bit annoying because you have to implement a method and then arena such. But yeah, probably mirror somewhere. But yeah, you can look at it. Yeah. Anyway. Yeah. Yeah. My solution is a bit different, but maybe it's eventually the same thing. But I don't use the concept of paths like this. But it's also n squared dt, so probably eventually the same. But yeah, maybe I can go through it a bit quickly. Basically, my solution is like, of course, dpij. It's the number of palindromes. Basically. Yeah, okay. Yeah, basically I have two DPs. One that says dpij is how many palindromes, but you can only choose these characters. And the other one is the one inside. Yeah. But then how do you handle the double counting and how do you handle the double counting and avoid an ON loop? So let's talk about the one that counts the number of palindromes inside. So let's say this is I, this is J, dpij. You want to compute dpij. So yeah, I have another parameter here, k, that tells which pointers can go. So if let's say k is 0, then only I can go there. Sorry, yeah, let's say. And then when k is 1, only this pointer can go there. When k is 2, both of them must go at the same speed. Yeah, and then when ai equals aj, you choose whether you take the ai and aj character or not, something like that. Yeah, and by doing this properly, you can avoid the double counting. Like, I need this additional parameter, so it's a constant, which tells me which pointer can move. And if you do this properly, you can avoid the double counting. Yeah, and then the other DP, the outward DP is similar, and then with these two DPs, you can answer the queries as well. And this K will like, yeah, you can try to figure out the recursion, but yeah, basically your DP will switch in the different value case a lot. Like if you go here and then you meet this J, you call DP with now K equals 2, something like that. And then from K equals 2, you choose whether you want to go K equals 0 or K equals 1, something like that. Yeah.
So what does that give you? What does the result of the DP mean?
How many palindromes with I and J?
Between I and J?
Yeah, and you have another one that goes outside. So how many palindromes if you only can use the string from 1 to I and j to I? It's the degree similar.
Not necessarily using I and J.
I think it's necessary if k is 0, j must be used, something like that. Yeah. If k is 2, not necessarily using I and j. Yeah. And by doing it properly, you can avoid the double counting, because otherwise handling the double counting is hard. Yeah.
And then how do you compute for each position?
Yeah, the idea is similar. So basically, you look where is the pair. So you look the j, where j is the pair of I, and then you can use this dt multiplies this dt. Yeah. Yeah, I have the code. I actually put it, but it's a long time ago when I do the round. So yeah, if you want to figure out more detail, like whether it's actually counting I and j or not, and how the transition in detail, I'll make it about it. I have the code. Yeah, this solution also works. Yeah, it's actually quite good. I never think of the path representation before. Any questions? Okay. Yeah. Yesterday I was lacking content. Like finished early. This time I was over. Actually, I have one more task, so we can save it for tomorrow. And it's, yeah, there's only just one more task. Yeah, we'll save it for tomorrow. So I'm going to skip slides. There's actually some slides in between. Okay, but we are and yeah, what I have for tomorrow is a bit short, so we can discuss this one tomorrow. And shouldn't be useful for the context anyway. So yeah, it's just another example task. Yeah. So any questions?
Will the content also be thematic?
Oh yeah, it's the same as yesterday. Like some of them will be thematic, some of them will be not. Oh yeah, I will actually tell you which days where it's non-thematic. If on the day it's just I steal from a context set, like the gold set, I'll let you. Oh, it's graphs. Graphs and some properties. Okay, yeah.